What does it mean to leave home? For tens of thousands of years, humanity's idea of leaving was measured in footsteps. A tribe leaving the valley, a fleet leaving the shore, a caravan disappearing into desert horizons. Each departure was a gamble, each journey an act of faith. Yet all of those departures had one thing in common: the possibility of return. But what happens when the horizon we aim for is not a mountain range, not an ocean, not even another planet, but infinity itself? This is the question that haunts astronomers, physicists, and dreamers alike. Will humans ever leave the solar system? It is a question both practical and philosophical. Practical, because our sun is not eternal. In 5 billion years it will swell into a red giant, boiling Earth's oceans into vapor. Philosophical, because to leave the solar system is to test the very boundaries of what it means to be human. When we say leave, what do we mean? Do we mean a single machine, like Voyager 1 already drifting into the void? Do we mean a human-built craft carrying generations of life beyond the heliosphere? Or do we mean something even more radical, the spreading of human consciousness in biological or digital form across the stars? The solar system is our cradle, but no cradle can hold the child forever. Yet the distance between the stars is so vast, the challenge so overwhelming, that leaving seems less like travel and more like mythology. And still the question lingers. So let us attempt an answer, not with a single explanation, but with a journey of our own. 10 steps into the unknown, each one carrying us farther from the familiar warmth of the sun toward the cold frontier of interstellar space. Our story begins with a map, not of countries, not of continents, but of the cosmic island we call home, the solar system. Close your eyes and imagine the Earth from orbit. Not the way you've seen it on maps or in photographs, but as a living, breathing sphere suspended in the darkness of space. A blue ocean wrapped in white swirls of cloud, glowing faintly against the infinite backdrop. From this vantage point, Earth feels small, fragile, even lonely. And yet Earth is not alone. It belongs to something larger, a cosmic family bound together by gravity, the solar system. To understand what it means to leave this family, to abandon the embrace of the sun, we must first see it for what it is, a celestial island in the vast ocean of the Milky Way. At the center of it all burns the sun, a sphere of plasma 1.4 million kilometers wide, its surface boiling at nearly 6,000 degrees Celsius, while its core rages at 15 million degrees. Hydrogen atoms, crushed under immense pressure, fuse into helium, releasing energy that has taken billions of years to sustain. This energy radiates outward, bathing the planets in light and warmth. Without it, Earth would be nothing more than a frozen rock drifting through the void. Every sunrise, every growing seed, every beating heart is powered by this nuclear inferno 150 million kilometers away. But the sun is more than our power source. It is the gravitational anchor of the solar system. Its invisible grip holds every world in place. Mercury with its blistering days, Venus with its toxic skies, Earth with its seas, Mars with its rust-red deserts, Jupiter with its giant storms, Saturn with its shimmering rings, Uranus tipped on its side, and Neptune at the outer frontier. Even the tiniest grains of dust and ice beyond Neptune owe their paths to the sun. In this sense, the solar system is like a great wheel, with the sun as the hub and the planets as spokes, forever circling in silent obedience. When most people imagine the solar system, they picture the 8 planets orbiting neatly around the sun. But that image is misleading, like seeing the shoreline of an island without realizing the waters stretch for thousands of miles beyond it. The true structure of our solar island is layered, each region stranger and more mysterious than the last. The inner planets, Mercury, Venus, Earth, Mars. Small, rocky, familiar. These are the lands we dream of visiting, with rockets and rovers. The asteroid belt, a scar between Mars and Jupiter. It is not, as movies sometimes suggest, a dense minefield of tumbling rocks. In reality, the asteroids are scattered across millions of kilometers, fragments of a world that never formed. The gas giants, Jupiter and Saturn, titans of hydrogen and helium, each surrounded by dozens of moons, some of which, like Europa and Titan, may harbor hidden oceans. The ice giants, Uranus and Neptune, pale blue orbs on the frontier, where sunlight is dim and seasons last decades. The Kuiper Belt. Beyond Neptune lies a ring of icy bodies: Pluto, Haumea, Makemake, Eris. These are remnants from the birth of the solar system, frozen fossils that hold the secrets of our origins. But even the Kuiper Belt is not the end. Far, far beyond, like a mist at the horizon, lies the Oort Cloud, a vast sphere of icy fragments, perhaps trillions of them, surrounding the Sun at distances up to 100,000 astronomical units. 1 astronomical unit, remember, is the distance from Earth to the Sun, 150 million kilometers. The Oort Cloud may stretch 100,000 times farther than that. It is here at this invisible boundary where the Sun's gravity weakens and the interstellar winds of the galaxy begin to dominate. This, more than Pluto or Neptune, is the edge of our island. Now pause for a moment and consider the scale. The Earth orbits the Sun at 1 astronomical unit. Neptune sits at 30. That means if Earth's orbit were the size of a coin, Neptune would be a meter away. The Oort Cloud, it would be nearly a kilometer away. Voyager 1, the fastest human-made object to leave Earth, is currently moving at about 17 kilometers per second. It took 35 years just to pass the heliopause, the bubble of space carved by the solar wind. And yet Voyager has not even come close to the Oort Cloud. At its current speed, it would take 14,000 years to reach the inner edge, and perhaps 40,000 to leave it completely. Leaving the solar system, in other words, is not like crossing an ocean. It is more like trying to walk across a continent while the land keeps stretching beneath your feet. The distances are so immense that our minds struggle to grasp them. Here is a sobering truth. If the solar system were shrunk so that Earth sat just 1 meter from the Sun, the nearest star, Proxima Centauri, would be more than 270 kilometers away. That is the scale of our isolation. But why speak of leaving at all? Isn't the solar system enough? The answer depends on perspective. On one hand, the solar system is vast, with countless moons, asteroids, and dwarf planets still unexplored. Humanity has not even set foot on Mars, let alone colonized Jupiter's moons or built stations in the Kuiper Belt. For many, these dreams alone are more than enough to occupy centuries. But on the other hand, the solar system is finite. Our Sun has a lifespan. In 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, perhaps even Earth. Long before that, in less than 1 billion years, its growing brightness will boil our oceans away. If humanity survives that long, we will have no choice but to move beyond the solar system or perish with it, even in the nearer T-End. There are reasons to look outward. Asteroid impacts, supervolcanoes, or human-made disasters could threaten our survival. To leave the solar system is to ensure humanity's story does not end with a single star. It is an act of insurance, but also of ambition, the natural extension of the same curiosity that once pushed us across rivers and oceans. In a sense, we have already begun. The Pioneer 10 and 11 spacecraft, launched in the 1970s, were the first to cross the orbits of the outer planets. Pioneer 10 has long since fallen silent, but it drifts outward still, carrying a plaque etched with symbols of humanity. Voyager 1 and 2, launched shortly after, carry golden records with music, greetings and images. Messages in a bottle cast into the galactic sea. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to truly enter interstellar space. New Horizons, launched in 2006, flew past Pluto in 2015 and continues its journey outward. Someday, thousands of years from now, it too will join the silent flotilla of machines beyond the Sun's reach. These probes are tiny, fragile, and uncrewed, yet they represent the first whispers of humanity beyond the island. They remind us that leaving is possible, but also unimaginably slow. So what holds us back? First, energy. Escaping Earth requires enormous fuel. Escaping the Sun's gravity well requires far more. Each additional kilometer per second of velocity demands exponentially more energy. Second, time. Even at Voyager's incredible speed, leaving the solar system takes tens of thousands of years. No human crew could survive such a journey. Third, protection. Space is not empty, it is filled with radiation, cosmic rays, and the constant threat of micrometeoroids. A ship designed to survive for millennia would be unlike anything we have ever built. In short, the solar system is not just a home, it is a fortress. Its walls are made not of stone but of scale, distance, energy, and time. And so we return to our question, will humans ever leave? The solar system is vast enough to seem infinite, yet fragile enough to demand escape. We are prisoners in a gilded cage, blessed with a star that sustains us, yet doomed by that same star's mortality. To leave this cage requires more than rockets. It requires imagination, patience, and perhaps an entirely new understanding of physics. But before we can imagine the future, we must examine the past, because humanity has already tried again and again to reach the frontier. Our next step is to look at these attempts, the pioneers, the voyagers, the new horizons, and to ask what lessons have they left us about the possibility of true escape. And so the question lingers like a hum in the silence, what have we already done to test these walls? Because for all the impossibility of leaving the solar system, humanity has never been content with staying still. Since the dawn of the space age, we have thrown machines like stones into the dark, hoping they would carry our curiosity beyond the warmth of the sun. They are fragile, small, and insignificant compared to the distances they face. And yet, they are our messengers, the first whispers of escape. If Chapter 1 showed us the fortress, then Chapter 2 is the story of the first cracks in its walls. It began in the 1970s. The world was still young in spacefaring years. Humanity had walked on the moon, but our reach beyond Earth was still tentative. The outer planets were mysterious distant worlds glimpsed only through telescopes. To send anything there seemed audacious. To send something beyond them, impossible. Yet in March 1972, a small spacecraft named Pioneer 10 lifted off from Cape Canaveral. It was no bigger than a refrigerator, but its mission was revolutionary: to fly past Jupiter and then continue outward forever. For the first time, a human machine was set on a course that would one day carry it into interstellar space. The symbolism was not lost on its makers. They attached a golden plaque engraved with simple symbols, a nude man and woman, the outline of the spacecraft, a map of pulsars pointing to Earth. It was both an instruction manual and a cosmic handshake, a way of saying, this is who we are, this is where we come from. In December 1973, Pioneer 10 flew past Jupiter, becoming the first spacecraft to cross the asteroid belt and gaze at the gas giant storms up close. Then it drifted outward, its signal growing fainter each year. By 2003, it had fallen silent. But silence does not mean stillness. Today, Pioneer 10 continues its voyage into the darkness, heading toward the constellation Taurus. It will reach the nearest star in that direction in about 2 million years. Think about that, a machine built by human hands, now a ghost in the night, destined to wander long after every human alive today has turned to dust. Launched just a year later, Pioneer 11 followed a similar mission. After Jupiter, it flew past Saturn, capturing the first close-up images of its rings. Then it too sailed outward. Its last faint signal was received in 1995, but like its twin, it remains on course toward the stars, a silent ambassador of human ambition. Together, the pioneers marked humanity's first attempts at true escape, not orbiting, not returning, but leaving. But if the pioneers were the first cracks in the wall, the Voyagers were the battering rams. Launched in 1977, Voyager 1 and Voyager 2 were built not just to leave the solar system, but to explore the outer planets in detail. Timing was everything. In the late 1970s, the outer planets were aligned in a rare formation that occurs only once every 176 years. With precise planning, a single spacecraft could use the gravity of one planet to slingshot to the next, saving enormous amounts of fuel. Voyager 2 took full advantage, visiting Jupiter, Saturn, Uranus, and Neptune, the only spacecraft ever to see them all. Voyager 1, on a slightly different trajectory, made close passes of Jupiter and Saturn before curving upward out of the solar plane. But the Voyagers carried something more precious than instruments. Each bore a golden record, a phonograph disc coated in gold, etched with 116 images, 90 minutes of music, greetings in 55 languages, and even the sound of a mother kissing her child. It was Carl Sagan's idea. If these machines were to drift forever, Let them carry a time capsule of humanity, a gift for any intelligence that might one day find them. On the cover of the record was a diagram showing how to play it, a map of pulsars pointing to Earth and the outline of a hydrogen atom. The message was humble, almost desperate. We were here. We wanted to be known. For decades, the Voyagers sailed outward, sending back data about the solar wind, cosmic rays, and magnetic fields. Their journeys became quieter after their planetary encounters, but their mission was not over. Scientists knew that at some distant point, the Voyagers would cross the heliopause, the boundary where the sun's solar wind yields to the interstellar medium. Voyager 1 reached this threshold in 2012. For the first time in history, a human-made object entered interstellar space. Not another planet, not another orbit, but the infinite sea between the stars. Voyager 2 followed in 2018. Both still send faint signals to Earth, requiring massive radio dishes to catch their whispers. Each year their power dwindles, but as long as they endure, they are humanity's furthest voices. And even when they fall silent, they will continue to travel, silent messengers carrying our story into eternity. In 2006, another mission joined the lineage, New Horizons. Its goal was different: to study Pluto, the most famous dwarf planet. After a 9-year journey, New Horizons flew past Pluto in 2015, revealing a world of frozen plains, icy mountains, and a heart-shaped glacier. It was a reminder that even at the edges of the solar system, beauty thrives. But New Horizons did not stop. It continued outward, passing another Kuiper Belt object called Arakoth in 2019. Today, it is still sailing toward interstellar space, though it will not reach the heliopause for decades. One day, like the Voyagers and Pioneers, it too will leave the sun behind. What do these attempts teach us? First, that escape is possible, not for humans yet, but for machines. We have already placed artifacts beyond the reach of the sun. Second, that time is the greatest barrier. The Voyagers, moving faster than any crewed spacecraft we have ever built, will take tens of thousands of years to reach the Oort Cloud. The nearest star is 4.24 light-years away. At Voyager's speed, it would take 70,000 years to arrive. Third, that leaving is not just a technical act, but a symbolic one. The plaques, the golden records, these are not scientific instruments. They are cultural artifacts, messages of identity. They prove that for humanity, leaving is not only about physics, but about meaning. There is something haunting about these missions. The Pioneers, Voyagers, and New Horizons are still traveling, but they are also still alone. No one will follow them for centuries, perhaps millennia. When they are finally found, if ever, the languages on their records may be forgotten. The civilizations that built them may no longer exist. And yet they endure. In a way, they are more immortal than we are. They will outlast cities, nations, even continents. They are humanity's first attempts at eternity. So when we ask, will humans ever leave the solar system? We must begin by acknowledging that in a sense we already have. Our machines have done what we cannot, slip the grip of the sun. But their journeys also highlight the scale of the challenge. For humans to follow, we need propulsion systems far beyond chemical rockets. We need ways to survive journeys lasting generations. We need to rethink not only technology, but time itself. The story of leaving does not end with the Voyagers. It only begins with them. The next chapter is about propulsion, the engines that could turn thousands of years into decades, the dreams of nuclear fire, antimatter sparks, and sails pushed by starlight. Because if Chapter 2 is the story of our first attempts, then Chapter 3 is the story of how we might truly succeed. The Voyagers, Pioneers, and New Horizons are already on their way outward, silent and steady. They've shown us that leaving is possible, but also that it takes thousands of years at their pace. Machines can endure such journeys, but humans cannot. And this brings us to the heart of the problem, the physics of escape. Because to truly leave the solar system is not just to dream of the stars, it is to confront the raw equations of gravity, motion, and energy. It is to ask, how much speed does it take? How much fuel? And above all, is it even possible with the laws of nature as we know them? Gravity is invisible, but it is absolute. Every object in the solar system dances to its pull. Every orbit, a compromise between falling toward the sun and flying away from it. To escape Earth's gravity, a spacecraft must reach 11.2 kilometers per second, Earth's escape velocity. That's already staggering. A bullet fired from a rifle leaves the muzzle at about 1 kilometer per second. Rockets must achieve more than 10 times that speed just to break free of our planet. But escaping Earth is only step one. The deeper prison is the Sun. To escape the solar system entirely, a spacecraft must travel at about 42 kilometers per second relative to the Sun. Voyager 1, with its gravity assists, reached about 17 kilometers per second, enough to slowly drift away, but not nearly fast enough to cross the void in anything like a human lifetime. Think of it this way: escaping Earth is like climbing a mountain. Escaping the Sun is like climbing a mountain that stretches forever into the sky. In spaceflight, speed is everything. And speed is expensive. Rockets carry fuel to accelerate, but the more fuel you carry, the heavier the rocket becomes, and the more fuel you need just to carry the fuel. This is the tyranny of the rocket equation, formulated by Konstantin Tsiolkovsky in the early 20th century. The equation is simple yet merciless. The change in velocity a rocket can achieve depends on the exhaust velocity of its engines and the ratio of its fuel mass to total mass. To reach higher speeds, you need exponentially more fuel. That's why chemical rockets, the kind we use today, are so limited. They're powerful, yes, but they can only achieve so much delta V change in velocity before the rocket becomes mostly fuel and almost no payload. It's why sending humans beyond Mars with chemical rockets seems daunting. Sending them beyond the solar system, almost impossible. And yet we have found ways to cheat. The Voyagers would never have reached their speeds without gravity assists, the technique of swinging past a planet and stealing a tiny fraction of its orbital momentum. Each slingshot gave them a boost, bending their path and flinging them outward faster than any rocket alone could achieve. Gravity assists are free energy, but they depend on alignment. Without the rare positioning of Jupiter, Saturn, Uranus and Neptune in the late 1970s, Voyager's grand tour would never have been possible. For human journeys, gravity assists might help, but they are not enough. We need engines that can burn for months, years, even decades, constantly accelerating until we reach speeds that make the stars feel nearer. And here lies the ultimate wall, the speed of light. Einstein's theory of relativity sets a universal limit. Nothing with mass can reach or exceed the speed of light, 299,792 kilometers per second. It is not just a matter of better fuel, it is a law of nature. The faster you go, the more energy you need. Approaching light speed requires infinite energy. This does not mean fast travel is impossible, but it does mean faster than light travel. Warp drives, wormholes, hyperspace remain speculation, not science. So the challenge is not just about breaking free of the sun, it's about how close to the speed of light we can reasonably get. 10%, 1%, even at 1/10 light speed, reaching Proxima Centauri would still take over 40 years. At 1%, it would take more than 400. These are timescales not of lifetimes, but of generations. Machines don't care about time. They drift, they endure. Humans do not. A human crew cannot survive a 40,000-year journey to another star. Even a 400-year journey strains the imagination. Could we build generation ships, vast self-sustaining habitats where entire societies live and die as the vessel drifts toward its destination? Could we master cryonics or suspended animation, freezing ourselves until we arrive? Each possibility creates new challenges. Food, energy, radiation shielding, mental health. Survival in interstellar space requires solving not just physics, but biology and psychology. The physics of escape is not only about rockets and velocities, it is about the limits of human life within the relentless framework of cosmic time. Let's consider energy. To accelerate a single kilogram of mass to 10%, the speed of light requires about 45 trillion joules of energy. That's roughly the amount of energy the entire world consumes in a day. Now imagine accelerating a spacecraft weighing hundreds of tons. The energy requirements become staggering. Nuclear bombs, antimatter, and massive solar arrays are all proposed solutions, but each carries its own near impossible challenges. Even if we could build such engines, even if we could harness such energy, there remains the problem of slowing down. Reaching another star is one thing. Stopping there, rather than blasting past it forever, requires just as much energy in reverse. At high speeds, space itself becomes dangerous. A grain of dust, harmless at low speeds, becomes lethal when struck at a significant fraction of light speed. Interstellar space is not empty. It is filled with cosmic rays, plasma, and drifting atoms. A ship moving at 10% light speed would collide with these particles at destructive energies. Shielding against this would require enormous mass, which adds more weight, which requires more energy, which loops back to the rocket equation. The walls of the fortress are not only distance and gravity, but the very fabric of space itself. And yet, to speak of impossibility is to misunderstand history. Humans have always faced impossible distances. Crossing oceans once seemed absurd. Flying through the skies was myth. Landing on the moon was science fiction. Each barrier fell when we reframed the problem, when we found new energy, new machines, new visions. The physics of escape looks unforgiving now, but perhaps in centuries to come the limits will look different, not broken, but bent by ingenuity. This is why the physics of escape is not the end of the story, but the beginning of imagination. If chemical rockets cannot carry us, what about ion drives, nuclear fusion, antimatter, or light sails? Each idea confronts the same physics, but in new ways. Each one dares to ask, can we cheat time? Can we push closer to light? Chapter 3 has shown us the wall. Chapter 4 will show us the tools we might use to climb it. B. Because the question is not only can we leave, but how. And the how leads us to propulsion. The engines of tomorrow, the dreams of today. We have stood before the wall. The physics of escape has shown us its scale. 42 kilometers per second to leave the sun, trillions of joules for even modest fractions of light speed, and dangers lurking in the void. It feels like a fortress we can never breach. And yet, humans are not defined by walls. We are defined by the ways we try to climb them. Chapter 3 gave us the problem. Chapter 4 is about the solutions, the engines that might one day hurl us beyond the solar system into the black ocean where the stars wait. Our story begins with the only propulsion system humanity has ever used to reach space: chemical rockets. The principle is simple. Burn fuel, expel exhaust at high velocity, and push forward in the opposite direction. From Tsiolkovsky's equations to the Saturn V that carried Apollo astronauts to the moon, chemical rockets have been our workhorses. But their limitations are severe. The exhaust velocity of chemical propellants is only a few kilometers per second. That means enormous amounts of fuel are required for even small changes in speed. The Saturn V, the largest rocket ever built, was 90% fuel by mass. Chemical rockets can launch us into orbit. They can send probes to Mars, Jupiter, even Pluto. But can they take us beyond the solar system? Not efficiently. To reach interstellar space with chemical propulsion would require rockets so massive and fuel-hungry that they are impractical. The Voyagers themselves relied on gravity assists, not raw rocket power, to gain their escape speed. Chemical rockets are a first step, not a final answer. If chemical engines are sprinters, ion thrusters are marathoners. Instead of burning fuel explosively, ion engines use electricity to accelerate charged particles, usually xenon ions, to extremely high speeds. The thrust is tiny, often no stronger than the weight of a sheet of paper resting on your hand. But the ease. An engine can run for months or years, slowly but steadily accelerating a spacecraft to much higher speeds than chemical rockets could achieve. NASA's Dawn spacecraft, launched in 2007, used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. It was not fast by interstellar standards, but it proved the concept. Slow acceleration can, over time, achieve remarkable journeys. Could ion thrusters carry us beyond the solar system? Perhaps, but their power comes from electricity, usually solar panels. Far from the sun, where light dwindles, they falter. Nuclear power could help, but the thrust remains small. Ion engines may serve as stepping stones, efficient for exploring the solar system, but too weak for interstellar leaps. If sunlight is not enough, what about the atom? Nuclear thermal propulsion, NTP, uses a nuclear reactor to superheat hydrogen and expel it through a nozzle. The result is far higher exhaust velocity than chemical fuel and far greater efficiency. The United States experimented with such engines in the 1960s under Project Nerva. Test reactors achieved promising results, but the program was cancelled before any spaceflight occurred. An NTP spacecraft could cut travel times to Mars in half, but for interstellar journeys, even nuclear thermal falls short. It is powerful, but not powerful enough to shorten thousands of years into human timescales. Still, it represents a bridge a technology within reach, a step toward the deeper future. Then there is a concept both audacious and terrifying, Project Orion. Proposed in the late 1950s, Orion envisioned propelling a spacecraft by detonating nuclear bombs behind it. A massive shock absorber would convert the blast into forward thrust. The numbers were staggering. Orion could, in theory, reach 10% the speed of light, fast enough to cross the distance to Alpha Centauri in about 40 years. For the first time, interstellar travel seemed imaginable. But Orion had problems. Launching such a craft from Earth would scatter radioactive fallout. The Partial Test Ban Treaty of 1963 effectively killed the project. Even if revived, the engineering challenges would be immense and the political barriers higher still. Yet Orion remains one of the few concepts that could actually deliver human-scale interstellar speeds with known physics. It is brutal, dangerous, and perhaps unthinkable, but not impossible. If fission bombs are crude hammers, fusion is the scalpel. Nuclear fusion, the same process that powers the sun, could, in theory, provide immense energy with less radiation and more efficiency than fission. A fusion engine could ignite pellets of hydrogen isotopes, expelling plasma at enormous speeds. The most famous design is the Daedalus project, proposed in the 1970s by the British Interplanetary Society. Daedalus envisioned a fusion-powered spacecraft, 2 kilometers long, capable of reaching 12% of light speed. The journey to Barnard's star, 6 light years away, would take 50 years. No fusion reactor has ever achieved net energy gain on Earth, let alone in space. But progress continues. If humanity cracks fusion, not just for power plants but for propulsion, the stars come tantalizingly closer. Go deeper into speculation and you find antimatter. When matter and antimatter meet, they annihilate completely, releasing pure energy according to Einstein's EXM. C2, just 1 gram of antimatter could produce the energy of a nuclear bomb. An antimatter rocket, in theory, could reach speeds close to the speed of light. It is the ultimate fuel, the holy grail of propulsion. The problem? Producing antimatter is incredibly difficult. All the antimatter ever made in human laboratories amounts to less than a few nanograms. Storing it safely is another nightmare, since any contact with normal matter triggers annihilation. For now, antimatter propulsion is a dream. But it is a dream rooted in real physics, not fantasy. If ever achieved, it could make interstellar travel practical. Not all propulsion requires fuel. Imagine a giant sail, kilometers wide, thinner than paper. Instead of catching wind, it catches light, photons from the sun, or lasers fired from Earth. Each photon carries momentum. Individually they are weak, but in numbers beyond counting, they can push a sail forward, slowly accelerating to incredible speeds. This is the idea behind solar sails and laser sails. Japan's Icaros mission proved the concept in 2010, unfurling a solar sail and riding sunlight across space. The Breakthrough Starshot project, funded in part by Stephen Hawking, proposes building tiny probes pushed by ground-based lasers to 20% light speed. At that velocity, they could reach Alpha Centauri in just 20 years. The challenges are immense, building sails large and strong enough, aiming lasers across light years, communicating with tiny probes. But unlike antimatter, solar sails are already real. They may be our best near-term shot at touching another star. Some concepts stretch even further. Warp drives, inspired by Einstein's relativity, propose bending space itself, contracting it in front of a ship, expanding it behind. In theory, this allows faster-than-light travel without breaking relativity, since the ship itself does not move faster than light relative to space. The most famous is the Alcubierre drive, proposed in 1994. The math works, but the energy requirements are astronomical, more than the mass of the universe, according to some estimates. Later refinements reduce this, but it remains far beyond our reach. Wormholes are another speculation, shortcuts through space-time connecting distant points of the universe. In principle, they could allow instant travel. In practice, they remain hypothetical, requiring exotic matter to stay open. These ideas live at the boundary of physics and imagination. They remind us that the laws we take for granted today may look different tomorrow. So where does this leave us? Chemical rockets are real but weak. Ion engines are efficient but slow. Nuclear propulsion is powerful but politically fraught. Fusion and antimatter remain dreams. Sails are promising but fragile. Warp drives belong to theory. The truth is that no single propulsion system today can guarantee our escape. Each is a piece of a puzzle we have yet to assemble. But the variety of ideas proves something important. Humans will not stop trying. The wall of physics is not a barrier but a challenge. And with every generation, the engines grow more ambitious. The story of propulsion leads naturally to a deeper truth, that even the best engines confront the same enemy, time. Whether we ride bombs, plasma, or photons, the journey to the stars will take decades, centuries, or more. For machines, this is fine. For humans, it is agony. Which brings us to the next chapter, time itself. How do we survive it? How do we carve songs? Fragile human lives across distances measured in centuries. Chapter 5 will take us from engines to endurance, from propulsion to persistence, because leaving the solar system is not only about how fast we go, it is about how long we can last. We have imagined the engines, from chemical rockets to antimatter dreams. Each propulsion system offers its own path toward the stars. Yet no matter how powerful, how elegant, how daring, all of them collide with the same wall, not of physics but of time, because the distances between the stars are not measured in kilometers alone, they are measured in lifetimes. If propulsion is the key, then time is the lock. And this chapter is about the ways humanity might one day try to turn it. Consider Voyager 1. It is the fastest spacecraft humanity has ever built, moving at 17 kilometers per second. Yet at that speed, it would take 70,000 years to reach the nearest star. 70 millennia. That is longer than all of recorded human history. If we somehow built a ship that traveled at 1/10 the speed of light, the journey to Proxima Centauri would still take more than 40 years. To more distant stars, hundreds or thousands. The scale is merciless. The nearest neighbor is unimaginably far. The galaxy itself is 100,000 light years across. If the solar system is an island, then the stars are continents scattered across an ocean wider than imagination. For machines, this is tolerable. A probe can drift silently for centuries, never aging, never tiring. For humans, it is a curse. We are creatures of decades, not millennia. Our bodies are fragile, our lifespans short. Time is the enemy that eats us alive long before the journey ends. To understand the challenge, imagine this. A crew of astronauts boards a starship bound for Alpha Centauri. Even if the ship traveled at 1% of light speed, an incredible feat, the journey would last over 4 centuries. By the time the ship arrives, every original crew member would be dead. Their children, grandchildren, great-grandchildren would inherit the mission, living and dying on a vessel they never chose to board. The destination would be reached by descendants who had never seen Earth, who knew only the walls of the ship and the hum of its engines. This is the concept of a generation ship. A generation ship is not just a spacecraft, it is a world. A sealed habitat carrying thousands of people, designed to be self-sustaining for centuries. Farms, water recycling, power systems, schools, hospitals, an entire civilization drifting between the stars. Science fiction has long explored the idea. Novels like Arthur C. Clarke's Rendezvous with Rama or Kim Stanley Robinson's Aurora imagine the perils and possibilities of such voyages. Scientists too have studied them, calculating the minimum population needed to avoid genetic collapse. Estimates range from a few hundred to a few thousand. The challenges are staggering. Food production must be endless. Machines must last centuries or be endlessly repaired. Social structures must prevent collapse or rebellion. The very meaning of purpose must be redefined, living not for oneself but for a destination one will never see. Psychologically, this may be the hardest problem of all. How do you maintain hope for a future that lies beyond your own death? How do you prevent despair, nihilism, or rebellion in a society doomed never to arrive? a generation ship is possible in theory. But in practice, it asks us to reinvent not just technology, but human culture itself. If we cannot live through the journey awake, perhaps we could sleep through it. Cryonics proposes freezing human bodies at extremely low temperatures, halting biological processes until revival. Suspended animation suggests slowing metabolism to near zero, perhaps with drugs or hibernation-like states. In nature, animals already achieve this. Bears hibernate for months, Arctic ground squirrels can survive with body temperatures below freezing, and certain frogs can be frozen solid and thawed back to life. If humans could mimic such states, interstellar travel becomes more manageable. Crews could sleep for decades, awakening only at the journey's end. Resources would last longer, generations would no longer need to pass the torch. But cryonics remains speculative. Freezing cells without ice damage is extremely difficult. Revival after decades, let alone centuries, has never been achieved. Suspended animation is closer, with NASA already testing ways to induce torpor in astronauts for long missions to Mars. Yet true stasis remains elusive. Still, the promise is profound: conquer sleep and you conquer time. Another solution sidesteps biology entirely. Send machines, not humans. Artificial intelligence does not age, does not hunger, does not despair. A probe with advanced AI could journey for centuries, arriving ready to build, explore, or even prepare a new home for eventual human colonists. In this vision, humans need not endure the journey at all. Instead, machines are our scouts, our builders, even our proxies. Perhaps one day, instead of flesh and blood settlers, it will be uploaded minds, digital consciousness, that make the voyage. This blurs the boundary of identity. If a copy of you exists on a starship, traveling while your body dies on Earth, is that still you? If humanity spreads by mind rather than body, have we truly left the solar system, or have we merely extended ourselves like shadows across the void? There is, however, one gift hidden in Einstein's equations: time dilation. At speeds close to light, time itself slows down for the traveler. A ship moving at 90% of light speed might take decades to reach another star from Earth's perspective, but for those aboard, only years would pass. The paradox is profound. From Earth's viewpoint, the journey takes centuries. From the crew's viewpoint, it is manageable. The price is enormous energy and unimaginable speed. But relativity at least offers hope. Time is not absolute. With enough velocity, we can bend it in our favor. Yet this only helps the travelers, not those left behind. To the people on Earth, their loved ones would be gone for centuries, their return impossible. Time dilation solves the journey, but it severs the connection to home. Even if we solve the biology of time with generation ships, suspended animation, or relativity, we still face the psychology of it. Humans are not good at waiting. Our minds crave immediacy, feedback, results within lifetimes. The idea of planting seeds that bloom centuries later is alien to us. And yet, we already live in such projects. Cathedrals took centuries to build, begun by one generation and finished by their great-grandchildren. The Long Now Foundation has designed a clock to tick for 10,000 years, a symbol of long-term thinking. Nations, cultures, religions, all are, in their way, generation ships, carrying values and ideas across centuries. Perhaps interstellar travel will require us to think the same way, to see ourselves not as individuals but as links in a chain, stewards of a mission larger than ourselves. And yet, no matter how we approach it, time remains the ultimate enemy. We can stretch it, bend it, endure it, sleep through it, but we cannot erase it. To leave the solar system is to confront the truth that the stars are not made for our scale. They are made for epochs, not decades, for civilizations, not lifetimes. Perhaps this is why the dream of interstellar travel feels both intoxicating and tragic. It asks us to reach beyond what we are built for. It forces us to imagine lives measured not by years, but by destinies. So far, we have faced the engines and the enemy. Propulsion gives us the means. Time resists the journey. But there is another challenge waiting, one that links both: survival itself. Even if we build the ships, even if we endure the years, how do we create worlds within worlds? How do we make the journey not only survivable, but livable? For that, we must turn to the next chapter, terraforming the journey itself. Habitats, ecosystems, and ships that are not just machines but homes, because leaving the solar system will not be a sprint, it will be a way of life. We ended the last chapter with a truth both sobering and undeniable. Time is the greatest enemy of interstellar travel. Even if we find engines that push us faster, and even if we master suspended animation or embrace generation ships, the journey itself must be endured. And this raises a deeper question: what will the ship itself be? It cannot simply be a rocket. It must be a world, a vessel not of weeks or months but of centuries, a place where humans are not just passengers but inhabitants, where life can thrive in the void between stars. This is the art of terraforming the journey, not terraforming planets but terraforming space itself, creating sustainable, living environments aboard ships that drift across light years. Imagine boarding such a vessel. You walk through corridors, not of steel alone but lined with gardens. Trees stretch toward artificial suns, rivers flow in controlled loops, children laugh in parks while outside, a vacuum colder than death waits. This is not a fantasy. It is the logical extension of what interstellar journeys demand. If humans are to live and die aboard ships, those ships must become worlds in miniature. Science fiction has long imagined this. O'Neill cylinders, Stanford Tory, vast habitats spinning to simulate gravity. These designs are not merely art, they are based on physics. A rotating cylinder kilometers wide could generate artificial gravity through centrifugal force. Farms could be grown along its walls. Cities could stretch along its rim. With sufficient energy, such habitats could support tens of thousands, perhaps millions of people. In such a ship, the voyage would no longer feel like a prison, it would feel like a planet. A smaller, artificial one, but one built to sustain the human spirit. But building walls is not enough. The heart of the challenge is life itself. Earth is not just a planet, it is a biosphere, a web of billions of organisms interacting in balance. Every breath you take relies on plants, microbes, oceans, and cycles older than civilization. Reproducing this balance in a sealed habitat is an immense task. We have tried, in small ways. Biosphere 2, an experiment in the 1990s, attempted to create a closed ecosystem under glass. It struggled, oxygen levels fell, species died, the balance proved fragile. In space, the stakes would be far higher. Oxygen must be regenerated, carbon dioxide must be scrubbed, water must be purified endlessly, food must be grown in limited soil, perhaps through hydroponics or vertical farms. Even bacteria must be managed, lest disease spread unchecked. The lesson is clear. A ship is not only an engineering project, but an ecological one, to terraform. And the journey, we must become gardeners of an artificial Earth. Beyond ecosystems lies another enemy, radiation. On Earth, we are shielded by our atmosphere and magnetic field. In interstellar space, no such protection exists. Cosmic rays and high-energy particles would bombard a ship endlessly, damaging DNA, increasing cancer risk, and degrading electronics. Solutions exist. Thick walls of water or regolith could shield against radiation. Magnetic fields could deflect particles. Rotating habitats could store radiation-shielding water in outer layers, doubling as protection and resource. But shielding is heavy, and every kilogram adds to the cost of launch. Here lies another paradox. The more we shield, the heavier the ship, the harder it is to propel. Terraforming the journey means solving this balance, survival against weight. Life requires energy. On Earth, the sun provides it freely, but beyond the solar system, sunlight dwindles to almost nothing. Ships will need artificial stars, reactors that burn for centuries. Nuclear fission could last decades, but for true interstellar voyages, fusion reactors may be essential. If humanity ever harnesses fusion, its near limitless energy could sustain not just engines, but entire biospheres. Imagine a ship with a fusion heart, a miniature sun at its core, powering lights, farms, and life. This is not fantasy, it is engineering scaled to cosmic proportions. Perhaps the hardest challenge of all is not physics, but psychology. Imagine being born on such a ship. The stars outside are points of light, unreachable in your lifetime. Earth is a story told in books. The destination is a promise you will never see. Would such a life feel meaningful, or would despair creep in as it did in Biosphere 2 when oxygen dwindled? Psychologists suggest purpose is the key. A generation ship would need not only technology, but culture, myths, rituals, and identities rooted in the mission, the voyage at sea. Elf would become sacred. The ship would not be a waiting room, but a home. This is why terraforming the journey is not only about biology, it is about philosophy. To survive centuries in transit, humans must see the ship as more than a machine. They must see it as their world. Yet perhaps we do not need full ecosystems at all. What if machines carried us instead? Robots could maintain a ship for centuries, repairing systems, tending crops, even raising children born en route. Artificial wombs, AI tutors, robotic farmers, all could sustain life without continuous human oversight. In this vision, the first human colonists of another star may be children raised by machines, nurtured in habitats built by their mechanical parents. Humanity would arrive not by surviving the journey directly, but by outsourcing endurance to our creations. It is a strange, unsettling thought, yet it may be the most practical form of terraforming the journey. Think of the metaphor. To terraform is to make Earth-like. But in this case, we would not terraform Mars or Europa. We would terraform the void itself. The journey becomes the destination, the ship becomes the planet. Perhaps this is the true step in leaving the solar system, not simply crossing space, but transforming it, turning the emptiness into something alive, something habitable, something human. And in doing so, we change what it means to be human. No longer bound to Earth, we become a species of builders, carrying fragments of Eden into the wilderness. So where does this lead us? Terraforming the journey solves survival, but not purpose. Even if we master ecosystems, radiation, and psychology, one question remains: where are we going? The solar system is vast, but beyond it lies the galaxy itself, a city of stars stretching into forever. If we build ships as worlds, what destination should they seek? What stars call to us most strongly? This brings us to the next step, the interstellar neighborhood. Because once we know how to live in transit, the next question is not if we can go, but where. And that is the story of Chapter 7. We have imagined the ship as a world, a garden sealed in steel, carrying life through the abyss. But a ship, no matter how perfect, is never built just to drift. It is built to arrive. And so the question sharpens: where do we go? Beyond the solar system lies the galaxy itself. A sprawling city of stars, 100 billion lights scattered across 100,000 light years. But galaxies are too vast to imagine. For our first steps, we must think smaller. We must ask what is in our neighborhood. Our sun is not solitary. It is part of a small cluster of stars moving together through the Milky Way. The closest of them is Proxima Centauri, a dim red dwarf only 4.24 light years away. To put that in perspective, if Earth were a marble and the sun sat 10 meters away, Proxima Centauri would be another marble nearly 300 kilometers down the road. Proxima Centauri is faint and small, only 1/8 the mass of the Sun, and yet in 2016 astronomers discovered something extraordinary: Proxima b, a planet orbiting within its star's habitable zone, a potentially Earth-like world closer than any other star. It may not be hospitable. Red dwarfs flare violently, bombarding their planets with radiation. Proxima b may be scorched, its atmosphere stripped away, or it may be shielded by magnetic fields and oceans harboring life beneath a sky tinged crimson. The truth is, we do not know, but its very existence changes everything. The nearest star has a planet that could, in principle, host life. If we ever leave the solar system, Proxima b will be the first target. Proxima is not alone. It is part of a triple system, Alpha Centauri A and B, two sun-like stars locked in a binary dance. At 437 light years away, they are bright, warm, and familiar. Alpha Centauri A is almost a twin of our Sun. Alpha Centauri B is slightly smaller and cooler. Together, they form a system that has long fascinated astronomers and dreamers. If planets exist there, and evidence suggests they might, they could be strikingly Earth-like. Imagine standing on a world in Alpha Centauri, looking up at two suns in the sky, their golden light overlapping in complex shadows. Imagine oceans reflecting twin sunsets. Imagine life unfolding not under one star, but two. The Centauri system is close enough that projects like Breakthrough Starshot specifically target it. Tiny probes pushed by lasers, racing at 20% the speed of light, could reach Alpha Centauri in 20 years. They would not carry humans, but they would be the first eyes to peer into another star system directly. Beyond Centauri lies Barnard's star, a red dwarf 6 light years away. It is older than the Sun, dim and ancient, one of the most studied stars in the sky. In 2018, astronomers announced a possible planet orbiting it, Barnard's Star B, a cold super-Earth near the snowline of its star. Even if icy, such worlds matter. They could host subsurface oceans or serve as stepping stones for future explorers. Then there is Wolf 359, a mere 7.8 light-years away. Faint, almost invisible to the naked eye, yet close enough to be part of humanity's first map beyond the sun. The lesson is clear. Our immediate neighborhood is crowded with red dwarfs. Small dim stars that make up 70% of the galaxy. Most are unstable, prone to flares. But they also host planets. The nearest ones already show us that Earth-like worlds may not be rare. In the past 3 decades, astronomy has undergone a revolution. We have discovered more than 5,000 exoplanets, worlds orbiting stars across the galaxy. Some are gas giants hugging their stars. Others are super-Earths, rocky and massive. A precious few sit in the habitable zones where liquid water could exist. The TRAPPIST-1 system, 40 light-years away, boasts 7 rocky planets, 3 of them in the habitable zone. Imagine an entire family of Earth-sized worlds circling a single star, close enough to travel between them like stepping stones. The Kepler 452 system, 1,400 light-years away, hosts a planet strikingly similar to Earth, orbiting a sun-like star. Too far to visit soon, but a tantalizing glimpse of what might exist nearer. The message is simple. Planets are everywhere. Life perhaps is not a miracle but a pattern. But a destination is not enough. Arriving at a star system raises questions as hard as the journey itself. How do we slow down after racing at a fraction of light speed? Without braking, a ship would scream past its target and vanish into the dark. The same energy used to accelerate must be spent to decelerate. And what if the planet we aim for proves hostile? A barren rock, a poisoned sky, a world unfit for life. Do we settle anyway, building domes and habitats? Do we terraform, reshaping entire planets over millennia? Terraforming is its own odyssey. Thickening an atmosphere, warming a frozen world, seeding life. These are not projects of decades, but of epochs. And yet, if humanity can endure the voyage, perhaps it can endure the reshaping of alien worlds. Perhaps the most haunting realization is this. The stars are not empty points, but nodes in a web of possibility. Each star, each planet is a shore, and between them stretches an ocean of darkness. We may never cross the galaxy in one leap. Instead, we may move step by step like ancient monks. Sailors hopping from island to island, first Proxima, then Alpha Centauri, then Barnard's Star. Slowly, painfully over millennia, humanity could spread outward, filling the local bubble with life. The interstellar neighborhood is not a map of destinations, but of stepping stones. Each reachable world makes the next reachable. Each ship that arrives can build the foundation for another to depart. But here lies the deeper question: why go at all? The solar system itself offers endless room for expansion. Moons of Jupiter and Saturn may be colonized. Mars could be terraformed. Asteroid belts mined. The Oort Cloud could host trillions in floating habitats. Why risk centuries of travel to reach another star? The answer lies in both survival and meaning. Survival, because no single star lasts forever. One day our sun will die, and only the stars will remain. Meaning, because exploration is woven into the fabric of what it means to be human. We are not content to look at distant lights and wonder. We are compelled to reach them. So the interstellar neighborhood tempts us with destinations. Proxima b, Alpha Centauri, Barnard's Star, each a possible shore, each a possible home. But knowing where to go is not enough. To truly attempt the journey, we must confront another frontier, one not of stars but of thought. Because behind every calculation of distance and velocity lies a deeper question. Why? Why leave the solar system at all? Why risk everything for the unknown? And this takes us to the next chapter, the philosophical challenge. For before we can answer how to leave, we must answer why. We have mapped the neighborhood. We know the nearest stars, Proxima Centauri, Alpha Centauri, Barnard's Star. We know they have planets, some even sitting in the habitable zones where water might flow. We have imagined ships that could carry us there, habitats that could sustain us, engines that could propel us. But before any of this matters, a question remains, not of physics, but of philosophy. Why should we go at all? Because technology answers the how, but purpose answers the why. And without the why, the how is meaningless. The first answer is brutally simple: survival. Our sun is not eternal. In 5 billion years, it will swell into a red giant, incinerating the inner planets. Long before that, its brightness will increase, boiling Earth's oceans and rendering it uninhabitable. But even without the sun's eventual death, dangers abound. An asteroid strike, a supervolcano, a gamma-ray burst, or even our own self-destruction through war or technology could erase life on Earth in an instant. To remain confined to a single star system is to gamble everything on one fragile basket. To spread to other stars is to ensure survival beyond disaster. Carl Sagan once wrote, "All civilizations become either spacefaring or extinct." Survival is not just an argument for leaving, it is the most compelling argument. But survival is not the only reason. Humanity is not a species that simply avoids death. It is a species that seeks meaning. From the first time a human left the cave to see what lay beyond the hill, curiosity has driven us forward. Oceans were crossed, continents discovered, skies conquered. Each time the answer was the same: we go because we must know. The stars are the final horizon. To look at them and not reach for them would be to deny what makes us human. In this sense, interstellar travel is not merely about survival, it is about becoming what we already are: explorers, storytellers, meaning makers. And yet, there is a counterpoint worth hearing. The solar system alone could sustain humanity for millennia. Mars could be terraformed, Venus could be cooled, asteroids could be mined to build habitats large enough to house trillions. The Oort Cloud holds enough material for civilizations beyond number. Why then risk centuries-long journeys when paradise could be built here? Why scatter ourselves across the stars when we have yet to master our own system? Some argue that interstellar travel is wasteful, even reckless, that humanity should learn to live within limits, to build inward rather than outward, that chasing stars is an escape from the responsibility of caring for the world we already have. The challenge is real. Going to the stars means dividing resources, attention, and willpower from problems on Earth: famine, poverty, climate change. Why dream of Proxima B while millions still suffer here? The philosophical challenge cuts both ways. To stay is to risk stagnation. To go is to risk neglect. Perhaps the truest answer lies deeper still, in the confrontation with meaning itself. For the first time in history, humanity faces the possibility that the universe is silent. Despite billions of stars and trillions of planets, we see no evidence of advanced civilizations. This is the Fermi paradox. If the galaxy is empty, then perhaps we are the only ones. If so, the burden of meaning falls on us. To remain bound to one world would be to waste a cosmic opportunity. To spread among the stars would be to give the universe a voice, to fill the silence with song. Nietzsche once warned that humanity must become something greater than itself, the Übermensch. Perhaps interstellar travel is that transformation, not an option but a destiny. But what if the universe is not empty? What if other civilizations exist, hidden or distant? The thought cuts two ways. It excites. Perhaps we could meet others, exchange ideas, join a galactic community. But it also terrifies. Contact could mean conflict. It could mean our destruction. The decision to leave the solar system is not just about survival or curiosity. It is about entering into the unknown where other intelligences might already lurk. Do we dare? Or do we stay hidden, safe in our island, hoping never to be noticed? In truth, the greatest challenge may not be the stars, but ourselves. To leave the solar system is to redefine what it means to be human. A generation ship would not carry us. It would carry descendants who might look different, think different, believe different. Given enough time, they may cease to be human in any recognizable sense. Is that acceptable? Is the goal survival of our biology, or survival of our culture, or survival of our consciousness in any form? If uploaded minds one day travel instead of bodies, is that still humanity? Or have we created something new, leaving ourselves behind? The stars do not just test our engines, they test our identity. And so the philosophical challenge can be distilled into a single tension: is it worth it? The cost of interstellar travel will be immense. Centuries of effort, fortunes in energy, perhaps entire generations sacrificed to ships they never chose. Yet the reward is uncertain. The nearest worlds may be barren, the galaxy may be silent, humanity may fracture in the attempt. And still, the dream remains. Perhaps the dream itself is the purpose. Perhaps reaching the stars is not about reward, but about proving we can. Because what is the alternative? To remain forever bound to one star, waiting for its death, to close our eyes to the infinite and pretend it does not call. That too is a choice, and perhaps the lesser one. So here we stand, at the crossroads of survival, curiosity, fear, and destiny. Each argument collides with the others, each is valid, and yet together they form a picture. The philosophical challenge is not to choose between staying or leaving, it is to recognize that both matter. That caring for Earth and reaching for the stars are not contradictions, but complements. One is the foundation, the other, the future. Which brings us to the next horizon. If leaving is not just an engineering project but a moral one, then the future depends on what tools we build. The engines, the habitats, the philosophies, all must merge into something greater. And that leads us to the next step in our journey, humanity's technological horizon. Because before we leave, we must first evolve. We ended the last chapter facing the philosophical challenge. Not just can we leave, but should we? Survival, curiosity, fear, and destiny all collide in the question of purpose. But purpose alone is not enough. To act on it, humanity must evolve, technologically, biologically, perhaps even spiritually. This is the horizon before us. The inventions, the breakthroughs, the transformations that could turn leaving the solar system from dream to reality. The first tool may not be engines or habitats, but minds, not human, but artificial. Already, machines calculate faster than we do, navigate spacecraft and analyze data from the farthest probes. But imagine AI designed not just as a tool, but as a steward of interstellar journeys. A ship traveling for centuries cannot rely on human oversight. Its systems must self-repair, adapt, make decisions without waiting decades for signals from Earth. This requires intelligence, flexible, resilient, creative. An AI captain could monitor life support, ration resources, repair damage, even raise new generations of humans aboard. In some visions, AI would not merely serve us, but be us, carrying uploaded human minds in digital form, free from the limits of biology. This raises questions of identity. If your consciousness is uploaded and sent across the stars, is it still you? If millions of copies travel, which one is real? Yet identity aside, AI may be our best bridge across the chasm of time. Hand in hand with AI comes robotics. A ship cannot survive centuries without repair. Micrometeoroids will scar its hull. Radiation will degrade its electronics. Habitats will need constant tending. Robots could serve as tireless maintainers, crawling along the exterior to patch damage, harvesting asteroids for raw materials, even building entire new habitats en route. Picture swarms of autonomous machines, each the size of an insect, maintaining ecosystems. Others the size of buildings, reshaping comets into water tanks or constructing new solar sails mid-flight. The ship becomes less a vessel and more a living machine, self-healing, self-evolving, guided by artificial caretakers. Yet even with machines, one obstacle remains: our own biology. Humans evolved for Earth, not for interstellar space. Gravity, radiation, isolation all erode our bodies. To survive, we may need to change ourselves. Genetic engineering could grant resistance to radiation, stronger immune systems, slower aging. CRISPR and other tools already allow us to edit genes with precision. In centuries to come, we may design humans tailored for space, able to thrive in low gravity, metabolize limited diets, even enter hibernation-like states. More radical still is synthetic biology, designing entirely new organisms to serve as companions, bioengineered crops to recycle waste, microbes to generate oxygen. Ships may become ecosystems, not of earthly species, but of engineered life forms adapted to the void. This raises profound ethical questions. If we change ourselves to survive the journey, are we still human, or are we creating a new species, one born for the stars, while Earthlings remain behind? Perhaps the answer is simple. Humanity has always evolved. Tools, fire, cities, machines, each has changed us. Leaving the solar system may simply accelerate the process. Another possibility lies not in changing ourselves, but in suspending ourselves. Cryonics, freezing the body at ultra-low temperatures, has long been a dream of futurists. If perfected, it could allow humans to survive journeys lasting centuries. Crews could sleep in capsules, awakening only at the destination. Even more advanced would be metabolic suppression, slowing the body's processes to a fraction of normal speed. Already, experiments with animals suggest possibility. As of induced torpor, if applied to humans, we could sleep not in ice but in slowed time. Cryonics and torpor are technologies of patience. They do not shorten the journey, they simply allow us to endure it without awareness of its length. All these tools, AI, robotics, biotechnology, depend on energy. And for energy, the most promising horizon is fusion. Fusion is the fire of the stars, the merging of hydrogen into helium, releasing immense energy. If humanity can harness fusion not only for power plants on Earth, but for engines in space, the leap to interstellar travel becomes far more realistic. Projects like ITER on Earth struggle toward net energy gain, but in time, fusion reactors small enough for spacecraft may emerge. Such engines could burn for decades, driving ships at a steady pace across the void, powering habitats with miniature suns. Fusion is not just an energy source, it is a symbol. To control the fire of stars is to step into the same category as stars themselves, creators of light in the dark. If humanity survives long enough, it may think on even larger scales. Physicist Freeman Dyson once proposed a Dyson sphere, a vast structure surrounding a star, capturing its total energy output. Not a solid shell, but a swarm of satellites orbiting in formation, harvesting starlight for civilization. Such megastructures remain speculative, but they represent a horizon of possibility. A civilization that can build on this scale, a Kardashev Type 2 civilization, could easily power interstellar fleets, terraform planets, or sustain billions in space habitats. The leap from Earth-bound humanity to Dyson-building humanity is vast, but if achieved, leaving the solar system would no longer be a question of survival, it would be a question of destiny. Some futurists speak of a technological singularity, a point where advances in AI, biotech, and energy accelerate beyond our comprehension. In such a future, problems that seem impossible today are inted. Stellar propulsion, cryonics, even faster than light travel might become trivial. This is speculation, yes, but it reminds us that technology does not evolve linearly. Breakthroughs come suddenly, shattering old limits. Fire, printing presses, electricity, computers, each rewrote the rules. Perhaps the horizon before us holds another such rewriting. Perhaps the barriers of distance and time will fall not by slow effort, but by sudden revelation. But with power comes choice. AI captains, engineered humans, cryonic sleepers, Dyson spheres, each carries risks. AI could drift beyond our control. Genetic engineering could divide humanity into castes, earthbound and starborn. Megastructures could exhaust resources or destabilize ecosystems. The technological horizon is not just about what we can do, but what we should do. The stars will test not only our physics, but our morality. Will we build wisely or recklessly? Will we remain one species or fracture into many? Will we use technology to preserve our humanity or to transcend it entirely? And so, we return to the question, will humans ever leave the solar system? If the answer is yes, it will not be because of rockets alone. It will be because we transformed ourselves, because we built minds in silicon, bodies in new forms, machines that heal themselves, habitats that are worlds unto themselves. Because we dared to step into the role of creators, not just travelers. The technological horizon is not a single invention, it is a spectrum of transformations, each carrying us closer to the stars. And beyond it lies the final vision. What happens when we truly succeed, when humanity, or what we become, finally takes that step into interstellar space? That is the story of the last chapter, Beyond the Solar Shore. We have walked a long road together, from the map of our solar island, through the first probes that dared to slip its edges, through the physics of escape and the engines of tomorrow, through time's merciless grip, through the habitats we must build, through the stars that beckon, through philosophy and technology alike. And now we arrive at the last question: what does it mean to truly leave? Because beyond all the mathematics and engineering lies a deeper truth. Leaving the solar system is not simply a matter of traveling far enough. It is a matter of transformation, of redefining humanity itself. Picture again the Earth from orbit, a blue marble, fragile and glowing. Now zoom outward, past Mars and Jupiter, past Neptune's pale blue glow, past the icy ruins of Pluto. Beyond lies the Kuiper Belt, a halo of frozen worlds. Beyond that, the Oort Cloud, a fog of comets stretching a light year into space. This is the true edge of the solar system. To pass it is to cross a shoreline. Behind lies the warmth of the sun. Ahead lies the black ocean of interstellar space, lit only by distant stars. The first to cross will not be humans but machines, as Voyager already has. But one day, perhaps centuries or millennia from now, a human-built world ship may drift across that boundary. It will not be a rocket, but a habitat, a self-contained ecosystem carrying life outward. Children may be born aboard, never knowing Earth except through memory and myth. That moment, when the first human or their descendant looks back and sees the sun as just another star, will be the true leaving. But what do we carry when we go? We will carry our technology, AI captains, robotic stewards, fusion hearts, engineered crops. We will carry ecosystems, oxygen cycling through plants, water through closed loops, food grown in hydroponic farms. We will carry culture, stories, languages, songs, might. Perhaps the Bible, the Quran, the Bhagavad Gita, the poetry of Homer, the music of Bach and the Beatles. Perhaps new stories written aboard the ships themselves, destined to outlast earthly traditions. We will carry identity, though it may change. Human bodies altered by genetic engineering, human minds uploaded into silicon, hybrid civilizations of flesh and machine. The passengers of the first starships may look at us as we look at Neanderthals, ancestors, but not quite the same. And yet through all this transformation, one thing will remain constant: the drive to continue. Suppose then that a ship arrives at Proxima b, or Alpha Centauri. What would that moment mean? It would not be a triumphant planting of flags like the moon landing. It would be quieter, slower, the opening of domes, the laying of foundations, the first breath of alien air, if breathable at all. It would be children playing under twin suns, their laughter echoing in habitats far from Earth. And yet, symbolically, it would be as profound as any moment in history. Humanity, once bound to one world, would now be a multi-stellar species. The solar system would no longer be a cradle, but a memory. The meaning of arrival is not the planet itself, but the fact of continuity. Life that began in Earth's oceans 4 billion years ago would now swim in alien seas. Consciousness born under one sun would now gaze upon another. To reach this point, humanity will have changed. We may not be recognizably human at all. Perhaps our descendants will be genetically engineered for low gravity or silicon-based minds, traveling at light speed as streams of data. Perhaps they will be hybrids of biology and AI, symbiotic forms adapted to the void. If so, have we lost ourselves, or have we fulfilled our destiny? The truth is that humanity has always been changing. Fire, language, agriculture, machines, each transformed us. The journey beyond the solar system will simply continue that process on a cosmic scale. What leaves the solar system may not be us exactly, but it will be the child of our mind, our dream, our will. And here lies a haunting possibility. Perhaps we will be the only ones. The galaxy is vast, yet silent. No signals, no beacons, no great civilizations. If the Fermi paradox is correct, we may be alone. If so, our leaving carries even greater weight. It will not just be survival or curiosity, it will be meaning itself. To step into interstellar space would be to ensure that the universe is not empty. That intelligence, life and wonder are not confined to one fragile star system. We would not just be explorers, we would be the voice of the cosmos, singing into the silence. Of course, there is another possibility: that we never leave, that we stagnate, content to live within the solar system, that wars or collapse destroy our progress, that our technology fails, or that we choose comfort over daring. If so, the stars will remain forever out of reach. Humanity will live and die under the same sun, never knowing the shores beyond. And one day, when the sun swells into a red giant, Earth will burn, and with it, our story. That is the cost of failing the challenge. Not just extinction, but wasted potential. But if we succeed, what then? Imagine the night sky 1,000 years from now. Not just one sun, but many. Each with worlds, each with civilizations, each carrying the legacy of Earth. Humanity spread not across one system, but dozens, hundreds. Communication slow, but culture enduring. Each star a new chapter in the same story. The solar system will remain our origin, but not our cage. The galaxy itself will become our home. This is what lies beyond the solar shore. Not conquest, but continuation. Not escape, but expansion. Not the abandonment of Earth, but the flowering of life into infinity. So, will humans ever leave the solar system? The honest answer is uncertain. Physics sets hard walls, time resists us, technology remains unproven, philosophy questions our motives, survival demands it, yet comfort tempts us to stay. And yet, if history teaches anything, it is that humans do not stop at horizons. From caves to continents, from oceans to orbits, each horizon has called and each has been crossed. The stars are the next horizon, and though the journey may take centuries, millennia, or transformations beyond recognition, the call will remain. One day, whether by machine, by mind, or by descendants, altered beyond what we now imagine, something that was once human will step beyond the Oort Cloud. It will look back at the sun, a pale dot behind, and forward at the galaxy, an ocean ahead. And it will know the question is answered. We have left